Good morning, everyone. We're having some technical difficulties. One of the organizers of this workshop is not able to join us. Maybe since the session has started, maybe he could join. Chaidan, are you able to hear us? Okay. Well, we'll get started. So this is the okay. Good morning, everyone, and welcome to the Open Knowledge Network workshop session at KGC. Hopefully, you could hear us. This is the tentative agenda for today. We'll start off with an introduction to the Open Knowledge Network. I am Jamin George. I'm one of the program directors within the National Science Foundation's Technology Innovation and Partnership Directorate. I am joined by Chaidan Baru, who is a senior advisor within the same directorate within the National Science Foundation. And we'll kick off this workshop with a quick introduction to the Open Knowledge Network. And then we'll move on to our first session where we have speakers from an NSF-funded program called the Convergence Accelerator. Within the Convergence Accelerator, we had invited close to two teams to give a talk about some of the activities they are part of that's been funded by the Convergence Accelerator program. Afterwards, we'll invite few industry presenters, folks from JP Morgan and Amazon. We'll talk about their thoughts on open standards and knowledge graphs. Then we'll take a quick 20-minute break. Then we'll get into a panel afterwards around 11:30, where we have invited 5 federal agency representatives to talk about how an open knowledge network would support their agency mission and facilitate their agency objectives and mission. For that panel, we have a representative from NOAA, NASA, and NIJ, National Institute of Justice, NIH, as well as USGS. After that panel, we'll break for lunch, roughly about for an hour. Then we'll come back for the second session of the workshop, where we talk about various tools and the current landscape of open knowledge network. We'll have folks from both academia and industry talk to us about that. And then we'll take a break and we'll get into the final session where we have a open discussion about how do we go about sustaining an effort that would build an open knowledge network. What are the various ways both industry as well as the government agency could partner to sustain such an effort. So that's the workshop in a nutshell. Yes, the workshop link has been shared in the chat. Thank you, Brian. Okay, so we'll get into a quick introduction to what Open Knowledge Network is. If I could. Trying to figure out. Yes, the vision for Open Knowledge Network started back in a interagency workshop organized back in 2017, 2016, where they put together the concept of Open Knowledge Network, which is basically the idea of taking openly available data, translating it into a graphical format, and attaching the relevant ontologies and taxonomy, the vocabulary needed to bring meaning and context to the data, and constructing knowledge graph, and then interlinking those knowledge graph using the idea of open knowledge network. And towards this vision, the National Science Foundation took their first step as part of their one of the Big 10 ideas, the idea called harnessing the data revolution. As part of this big idea, they published their vision and announced opportunities for people to submit their ideas. Basically, the concept of networking public data to power the next wave of AI, artificial intelligence, while addressing various societal challenges. And to make this vision a reality, the NSF tapped a relatively new program called the Convergence Accelerator. And as part of this Convergence Accelerator program, their inaugural track A, focused on Open Knowledge Network. And the opportunity was announced in 2019, and late 2019, they selected 21 phase 1 teams or projects to propose their concept for an open knowledge network. And roughly after a year, those phase 1 teams were down selected to phase 2 teams to actually build a prototype to further develop their prototype version of an open knowledge network. And we have invited almost all of those 5 phase 1 teams to talk next. So they give you a little bit more context as to the type of project and effort they are currently involved in. So that was the first step towards this idea of open knowledge network. The second step was in partnership with the Office of Science and Technology Policy from White House, NSF organized a innovation sprint last year, started in February, ran all the way through June 2022. And as part of this innovation sprint, NSF brought together representatives from industry, academia, as well as government agency to discuss where is the current opportunities and challenges involved in building an actual prototype version of an open knowledge network. Again, it's not just building individual knowledge graph, even though that's part of it. It is networking this knowledge graph to bring about new capabilities and opportunities for the data users. So at the end of that innovation sprint, the participants, roughly about 200 participants, contributed to a roadmap, which we published back in September 2022, that outlined the findings of the innovation sprint. So that was the second step. The third step currently that is ongoing is that 2 months ago, back in March this year, 2023, NSF announced an opportunity to actually build a prototype version of this open knowledge network. And the solicitation was announced in March. And the deadline to submit the proposals are in June 20th. We'll quickly introduce the program vision and goal. The program goal is to actually build a prototype version of an integrated data and knowledge infrastructure called the Open Knowledge Network. So we are looking to create a platform that would empower the government and non-government users, especially the users who will rely on the data to make decisions. And we envision that this will fuel the evidence-based policy making, continuing a strong economic growth for the future, as well as game-changing scientific breakthroughs. And all this will happen as well, at the same time, and this effort trying to address some sort of societal challenges, whether that is originating from climate change or social equity. This effort is actually a multi-agency effort, mainly by representative agencies, the federal agencies whose mission is to collect and make open data publicly available. So agencies such as NASA, NIH, NIJ, NOAA, and USGS has partnered with us. These agency representatives are here today. And we later today in the morning session, we do have a federal agency panel where these representatives will talk to you about their agency interest in the concept of an open knowledge network and how an open knowledge network would support their agency mission. And I think that's all I have at this point. And if there is, maybe I'll tell you a little bit about the actual program structure itself too. Now the program is program meaning the recently announced Proto-OKN opportunity consists of 3 themes. Again, this Proto-OKN program was informed by the roadmap report that we published back in September 2022, which was written by the participants of the innovation sprint that we had. So this program has 3 themes. Theme 1, where we are asking folks to build new knowledge graphs that would address a societal challenge and making use of federal agency provided data so that it would be supporting that agency mission. So all these agencies that I mentioned in my previous slide have their own data um, made available for the public to make use of, and they have provided their particular use cases those data could address. So we are looking for folks to maybe submit their ideas for how to make use of that data to address the particular agency use cases. So that's theme one, and we are also looking for uh, teams to talk about their ideas on how to bring about interconnecting these individual knowledge graphs. Um, so roughly, we're looking to fund two teams who's interested in proposing their ideas or how to uh, build an interconnecting fabric that would facilitate the um, uh, interconnection of various knowledge graph built by Theme One. And then yesterday I was in a session where people were talking about a training material and educational resources for building knowledge graph. We are also interested in those type of products, and we would like to hear from people on their ideas on how to build training material as well as education and outreach material needed to engage the users, make better user interfaces pretty much, and provide the needed background information to the user so they could interact with the prototype open knowledge network in an efficient manner. So we are also interested in that. So that's pretty much the program structure. And at this point, I will stop and see if there are folks who would like to ask questions or try to see if the co-organizer is able to speak. Uh, yep. I see Chayden as a speaker, so he should be able to talk at this point. Any questions, comments? Are you looking?
Can you hear me now, Jamin?
Yes, I could hear you and I could see you. Good.
Okay. It turns out they didn't send me the right link. Anyway, so I'm here now if there are any questions or comments.
Yes. If you want to bring up your slide deck, and we still have 10 minutes left for this opening session. If you want anything else that you wanted to cover, or even talk to some points that I may have missed, that would be good.
Let's see. How do I present to audience? Okay, so I had basically the same slides that you presented. Did you go through the sort of how we got here slide?
Yeah, very, very briefly, starting with the Big Ten ideas.
Yeah, okay, that's fine. So maybe the only thing I'll say is, as you heard, there is a solicitation out right now from NSF. In some sense, we think of this as phase three. You would have heard that Jamin talk about the convergence accelerator, which is a effort to kind of move research ideas into practice. And the first track was, of course, Open Knowledge Network. We funded, as you heard all this, just to recap very quickly, we funded about 20 projects in track phase one of that, of which 5 were sub-selected. You'll hear from some of them today. 5 were into phase two. But now what we are interested in doing is to see, to sort of continue to create a community around this and see how we can sustain this effort going forward. So we're trying to do this in a very intentional way. The solicitation is out right now for proposals that will be 3 years duration. So in some sense, we have 3 years of runway to try and make this happen. Our strategy here has, at least for now, is to connect with our agency friends, federal agency friends. Yeah, NSF is what we call, it's not a mission agency. NSF's mission is simply to fund research. So 94% of the money that comes to NSF goes out of NSF. 6% is basically to run the agency, but all the other agencies in the government have are mission agencies, and they have missions to fulfill and execute and so on. So our idea is, if we can connect this notion to the mission agencies, that could be a path to sustainability. And as you've heard, maybe from Jemin, and I think you'll hear for the rest of the day today, and certainly we are hearing it at the conference. I'm physically at the conference. I've been here yesterday. There is, I don't know if you want to think of it as a resurgence, but certainly a lot of interest. I think the timing is right to think about knowledge graphs. Some of us, of course, have been in the community for a long time, and we think maybe we're revisiting, but I think really it is a time when this kind of technology is becoming very, very central, and actually the introduction of large language models only makes it even more so, not less. So that's where we are, and I think I'll stop with that. See if there are any questions.
Um, so I have a question. As we build the knowledge graphs, and there be already from your phase 2, there are a number of knowledge graphs built. Um, uh, how about ensuring that um, the the robust use of knowledge graphs for the chosen community is also supported? So what I mean, as an example, we now are building this neurosymbolic approaches systems where knowledge graphs are incorporated into the AI models. So it's not just a matter of creating knowledge graph, but making it very easy and effective to make it possible for the machine learning pipeline to incorporate the knowledge graph, not just for a human users to query the knowledge graph or visualize it, but for the so does that sound appropriate for some of the work you see happening, maybe at least for the type 2 or 3 projects?
Yeah, that's a good question. And this, again, I would say it has come up already yesterday in this meeting, and I suspect it'll keep coming up through the days. Is that at the end of the day, this is not a technological problem, right? As we all understand, it's real. Well, I think of it as a socio-technical, but it's really a use case problem, is the way I think of it. At least where we stand right now, in order for us to get traction, we have to get users who really see this as part of their critical path, right? We want to see users who say, "I need this stuff." Whether it's USGS, since Dahlia is sitting right here across from me, or NIH and so on, they have to say, "I need this stuff," right? Then they will be committed to it. So any example you give, including use of graph-based machine learning or use of this in machine learning, I think the first thing we are looking for is, okay, who's the user who wants this, right? And who's saying, my life is just not, my life will get better if I use this, and my life is miserable right now. So that's kind of why theme one is there. Theme two automatically follows because, again, as engineers and computer scientists, we say, okay, I don't want to create, there is a common substrate we can create for all of those use cases, and that's what we are going after. But I think it has to be motivated by the use case. And so, I think, yes, more or less to what you're saying, but maybe just a caution that we don't want the technology to lead, we want the use case to lead.
Well, but I think one has to really build practical use cases and put it out there. And it may not be initially from one of the agencies; it may be from industry, community of users from industry. So,
That's fine. I mean, I think any realistic use case, but we are not, as I think even the solicitation says, that's an important point as well. We have 5 agencies listed on the front page, another 4 are mentioned in the solicitation. That doesn't mean those are the only ones.
mm,
So, any credible application. But once again, we are not interested. In some sense, you can think that's why I call it phase 3. We're thinking of, we want this to start closing down rather than opening up, right? So, we're not interested in funding brand new things once again that have no, that I say, oh, now I need a phase 4 to keep this going, right? The phase 3 is it. If we can't keep this going after 3 years, that means there is really no interest in doing this. We can think of it that way. I guess we have a couple more minutes for any comment or question. And I think Jamin mentioned the themes and the deliverables, and so it is our intention to be very intentional in this. So we hope to be very hands-on, and at the end of the day, it's not going to be a huge number of projects that are funded. So we want them all to sort of cozy up to each other. It's not easy. None of this stuff is easy. The 5 projects we funded in track A has not been easy to keep them together, and that was only 5, though there were 5 pretty big projects. Now we're talking about maybe 10 efforts that we want to try and keep together. So this is all about seeing if we can keep stuff together, create a community, and create something that keeps going. I guess we can flip to the next presentation, Jevin.
Yes. The next is the session 1, where we invite the Convergence Accelerator, Track A, and industry folks to give a quick 20-minute presentation, and followed by the 5-minute Q&A. First, we have combining ontologies with AI to synthesize summaries of technical documents. Adam and Doug, I've seen you guys here. Can you share your screen?
It looks like yeah, now I can. Yep, there we go.
Yes.
So I'm going to start by talking for 10 minutes, then I'll turn it over to Adam. So my name's Doug Downey. I'm from the Allen Institute for AI, and I'm going to talk about a project of applying ontologies and knowledge graphs and natural language processing to help summarize legal documents. This was a large collaboration of a bunch of different kinds of people. I don't think this would have happened without the Convergence Accelerator program. It's a very disparate kind of group that happened to come together through this program. A bunch of lawyers on this project. I'm a natural language processing researcher. Adam, who we'll talk to you in a second, is from a business school. So a fun collaboration of a bunch of different kinds of folks. I want to start by describing what legal documents look like. And here I'm talking about documents that describe civil rights cases. So there are these things called dockets that capture the main events of the case. There are complaints that people make that cause the case to happen, opinions issued about the case, and then there can be settlements or agreements at the end of the case. Altogether, there's a huge amount of text that describes even a single legal case, and there are thousands and thousands of these cases. So if you, for example, wanted to study civil rights cases, you might really appreciate a succinct summary of what went on in a case that you could read in a few hundred words that would tell you the key details without having to sort through all those documents. And this is the service that the Civil Rights Litigation Clearinghouse at the University of Michigan provides for civil rights cases. So lawyers who are carefully trained on this task of summarizing and pulling out key facts about legal cases populate that information into this repository, and this is of great value to the public and to legal scholars. But here's the problem. Like I mentioned, there's a ton of text associated with each case, hundreds of pages, tens of thousands of words, and as a result, it's very expensive to produce these summaries. So trained experts have to spend 1 to 10 hours, depending on the complexity of the case, to summarize these things succinctly. So this is where we stepped in as a natural language processing research group at the Allen Institute. We looked at this problem and thought, can we actually improve this situation by applying natural language processing technology. And like you often do in these cases, we started by building a data set that could be used to train and evaluate automated summarization systems applied to these legal cases. So we call that data set multi-lexsum, and it has a few distinguishing features, and I'll say a little bit more about this. So it's a real-world summarization data set. This is summary creation that's happening by people in the real world. It's not created just to study natural language processing. That can have a number of advantages. These are very high quality summaries. They're written by experts who are carefully trained. And as I'll describe in a second, we get these summaries at multiple levels of granularity because of what the Civil Rights Litigation Clearinghouse is aiming to do, and that presents new opportunities for natural language processing. So the value of this data set is twofold. So we hope that it can provide value to legal practitioners by streamlining and accelerating the process of writing these summaries that will help people understand lawsuits more quickly, help the public and other free law projects. And then we also hope that this data set has value for NLP researchers because it has some characteristics that make it different from existing NLP data sets today. So here's how humans create the summaries that are in the Civil Rights Litigation Clearinghouse. They take this huge set of input documents and they read those and they carefully write a long summary of about 600 or so words. From that and the source documents, they also compose a shorter summary. And then finally, there's a tiny summary that's normally used to tweet about the case. So these are the 3 levels of granularity of summary that we get. And all along the way, there are experts, there's an expertly curated set of guidelines about how these summaries should be written. And each person writing these summaries is trained to write them according to these guidelines. And typically the summaries are checked by a second expert before they actually end up on the site. So as summarization data sets go, this is like a really high quality one. And that's probably because it wasn't built to support natural language processing. It was built to actually summarize legal cases, in the real world, and that's why it's so high quality. But it presents a really unique opportunity for studying summarization. It was produced at great expense, so hundreds of experts over many years. The University of Michigan did this work, and here are the names of the folks who were involved in creating those summaries. Their names are small, but our appreciation for their work is massive. So once we've collected all these summaries from the Civil Rights Litigation Clearinghouse, it has some important properties. So like I said, this is authored by experts. A lot of summarization data sets don't have that characteristic. Having summaries for the same source data at multiple levels of granularity, long, short, and tiny, is exciting and presents an opportunity to study different types of summarization. We did a little bit of that work in the paper associated with multi-lexsum. I'd encourage you to take a look at that. The context length, that is the set of the source documents, much longer in this case than typical summarization data sets. And also the summaries themselves are longer than a lot of summarization tasks that are studied with existing data sets. And here's a table sort of describing where multi-lexsum sits among other summarization data sets. You can see it's got some unique characteristics, the ones I just mentioned on the previous slide. Okay, so here's where we stand. If we actually go and try to apply good summarizers to this task, and this is with models of the about 500 million kind of model size, give or take, we get a lot of hallucinations. So models of that scale actually don't do very well on this task. We get a lot of factually incorrect statements that are made by the models, and then a lot of unsupported claims. And if we try to put this summarizer into the workflow of the Civil Rights Litigation Clearinghouse, it's not helpful. So we asked the people to rate the summaries. They said, yeah, on a scale from 0 to 3, I give it about 0.4. So summarization technology of about a year or two ago is really not sufficient to tackle this task. We are currently doing experiments with GPT size language models, and they're better, but I don't think the problem is solved. What we're excited about, and this is before I turn it over to Adam, is using the knowledge graphs that were built by the Scales team from the Knowledge Accelerator, which is focused on ontologizing legal cases in order to improve these summaries. So most summaries have a set of key ingredients in them. It's like a legal case tends to have a handful of core fields that characterize the proceedings of the case. And a good knowledge graph would include these. And it's possible to extract some of these at actually really high accuracy, as Adam may describe. And if we could use those extractions, maybe we could do a much better job. So we are currently looking at this problem, and I can say, although this is very preliminary, putting in some of the Scales extractions into a GPT-4 size summarizer. So now we're talking about much better summarizers. Those ontologies are showing the potential of improving performance. This result is so preliminary that I hesitate to mention it, but we are seeing some promising early signs from large language models when we add this ontology information. Okay, that's all I've got. You can get the data set and use it right now. It's publicly available. Thanks, and I'll turn it over to Adam.
Thanks, Doug. I'm glad that you went with it, even though it's preliminary. And I am sharing the wrong screen. How do I? No, we do not want that. Well, I'm sorry, everyone.
Not a problem, Adam. While Adam figure out how to bring up his slide deck, we have a question in the chat, Doug. What is the context window for these models? Are you able to fit in a full source document to get a summary?
Great question. So yeah, we evaluate different models with different context lengths in the paper. In general, we're not able to fit all of the context into the model, and more context is helpful. We show that result in the paper. So yeah, context length is a limitation. I think in the paper we didn't go up larger than 4096, although I'd have to go back and check. Those details are in the paper. But yeah, context length and model capacity is a problem for us.
There we go. Can everyone see my slides now?
Yes.
Perfect. Okay. So going along with what Doug was talking about, a big part about why this is so hard is just related to our source domain of legal documents themselves and our understanding of litigation. One of the most fundamental things, especially for us as lay people, is this idea of, right, how many court cases settle. This seems to be a very simplistic aspect of documenting how the justice system works. And what brought me into this domain was just this little question I had. I had this belief, like most people do, you hear these facts like 98% of cases settle or almost all cases settle. And the reality is if you actually talk to lawyers, they don't actually know what the exact percentage is. They are inferring this because they think that less and less cases are, going to trial, but how cases are proceeding and ending aren't very well documented. And when people actually go and look at this and look at the data, there's lots of different interpretations depending upon how you are using what is available as data. Some people have looked at this and they would say, well, based on the administrative data we have, it actually looks like fewer cases are settling now than they did 50 years ago. And a lot of that comes back to the fact that there is no comprehensive, reliable data here. When we go through the administrative data we do have that summarizes how cases are working their way through federal courts, researchers find that there's a huge amount of error in this. What we currently have as available, prior to our efforts as funded by the National Science Foundation, is the integrated database that the Federal Judicial Center publishes. So this is an administrative data set where, like a lot of things in this domain, the courts themselves are documenting cases and then pushing essentially Excel spreadsheets to the Federal Judicial Center to collate and then publish as one data set for all 94 courts. One of the problems is there's a lot that goes on in these cases, but there's only one label, because this is essentially an Excel spreadsheet, that says how it ends, and it's very unclear what the difference is between these labels. This is a difficulty because when you actually work with these cases and these documents, the reality is that there's this massive forking path of how litigation can actually proceed from the initial complaint. There's motions to dismiss. Parts of the motions can be granted. Some causes and complaints will go all the way to the end. Others will be actually tossed from the case. And this is one of the difficulties in understanding. This is a very complex problem that requires a lot of nuance. And so that's what we've been working on, actually ontologizing. So our goal is just to enable our users, legal scholars, legal aid organizations, journalists, to answer the following types of questions about, what's happening in court, how do cases conclude, and how do essentially cases travel from beginning to end, and layering in all of the other entities that participate in it. The courts and the data is actually a live operational system. There is the theory about how cases should proceed, which is what lawyers are taught. So there are the federal rules of civil procedure that says these are all the things that a lawyer can do, that a judge can do in a case. As data practitioners, we know that there is a far more harsh reality. Bilateral settlement is one rule, one way that a case can actually conclude. But if you go to the source data itself, all of these docket entries that I have on the screen are all bilateral settlement. There's a huge number of parties and entities that are involved in these cases. The lawyers, the clerks, the judges, and they are all entering data to describe the case into one system, one live operational system. And there's no rules about how they have to rate this. And so this is what we've been working on, is trying to actually build large language models that can read through the text of these cases and apply our ontological labels to make it easier for further efforts, either systematic analysis or case summarization. There is a massive world of what could happen. So we have focused all along on our minimum viable product of an ontology that really describes the pathway from beginning to end. We have our case beginning, and there's a number of ways it can begin. The answer is from the counterparty, discovery, and then our dispositive events. What we've done to make this actually workable is working with our team, which includes a large number of lawyers. So we have over 750,000 of these cases in our database. And what we've done is essentially had all of these docket entries available, and we have essentially our legal team work through our idea of, okay, this is a beginning of an ontological label. This is how a case can begin. And they come up with some basic ideas and keywords of what would describe this as to how it would show up. So we go through some iterative steps of applying keywords and doing manual review to see how we do, going back and forth until we finally have enough of a training data set where we then stand up our large language models and then actually do the predictions and training. We built an entire system around this so that we can easily see, given keywords, what docket entries we will capture or won't capture, and what docket entries our models are capturing, so that we can kind of boil the ocean down to just see what are the edge cases or unique phrasings that we may be missing because of a certain court or clerk, and create these data sets for our human lawyers to annotate. We have over almost 100 individual classification models, and we have one giant model that we're about to publish that includes multi-classification of all of those. We have really good model performance in actually applying these labels to all of the dockets and docket entries. And when we look at our key events, like how the cases are ending, we have extremely high F scores, typically in the 90s%, although all of this is still almost finished, but not quite there. And if you do the comparison to what we can actually see through administrative data, we can actually identify the differences, something that's actually been pointed out with how fuzzy those labels are. We see a big difference in just actually identifying how many cases are settled in our repository based off of looking at the actual docket text in comparison to the administrative data set. It's about 12% more cases. And so what we're excited about is not just looking at this in the end with the essentially total summarization, but in actually understanding how they get to that ending. So now we are, for the first time, really able to track how the case begins to how the actual case ends and what's the pathway that it takes. This is being layered in our knowledge graph of what composes a case. So now we have these litigation event ontology predictions added on and annotating every single docket entry whenever and wherever they apply. And that's what we're excited about in terms of doing this partnership with Doug at the Allen Institute and his team, is we're getting a lot of things for free that we can add into that model, right? These event labels, because they're coming from the ontology, immediately signify their potential importance, right? How a case ends is more important than some random administrative motion in the middle. We're able to pull out what entity is performing that action. And we can group essentially event label and proximity and time between key events to try to bundle them together as additional metadata for model summarization. And so we're really hoping that we can use all of these features of the ontology and the applied labels to help fix some hallucination in the summarization model. And thank you. That's it. We'll take any questions.
I believe Doug already answered a few questions we had in the chat.
Okay. Are we out of time? Sorry for the technological mishap.
We still got 3 minutes, right, Jaden?
Yes, we do. We have a few minutes for questions. Actually, meanwhile, if the next person wants to get ready, is that Sergio?
Yes. Sergio, Lilith, and Yano.
Yeah, there was there were some questions in the chat so that were answered. That's good. And I saw the note from Enrel. I guess that was David. So please do contact us. We can talk about how maybe you can be part of this.
I want to follow up to Vinit's question on using the same tools for summarizing scientific documents, Doug. Um, you said doing multiple papers is much harder. Is that because are you referring to doing multiple papers simultaneously? And also, when you summarize technical papers, how do you handle the complex content in the sense of equations and pseudocode and all that?
Great question. So yeah, with multiple papers, I mean, yeah, comparing and contrasting across multiple papers, saying how one paper builds on another. Somebody gives you 5 papers and says, what does this body of research say? That's I think really tough to synthesize across the multiple papers, or maybe all 5 of them describe the same concept, and you want to kind of synthesize that into one really good description of the concept. That I think is tougher. I don't think we've looked too much at mathematics or pseudocode. It's an interesting question. Often for document level summaries like abstracts, you don't have to dig into those details as much, but with the ability of GPT-4 to actually do quite a good job working with code or with math, there might be really interesting new opportunities there. I'd love to take a closer look at that.
Yeah.
Thank you.
And I guess I will just say, I'm seeing the chat. We had this idea as just kind of it should be generally applicable, right? Legal documents are just like any other expert domain data source, right? It's understandable to people that are trained in it, and basically like gobbledygook jargon to anyone that's not. And so the idea here is just, of course, we have the raw data, but how do we efficiently combine that raw data with something that is kind of structured knowledge around it, like the ontology, to best combine that to get something better in terms of summarization? I mean, this is the classic problem of it takes experts to write summaries, and it takes way too much time for experts to do that for everything, for the lay public or even other people.
Thank you. Sergio, you want to bring up your screen?
Sure. Hi, everyone. So just to checking, Jamin, my time is
20 minutes.
20 minutes. And are Jana or Lilith joining, or I'm representing all three?
You're representing all three, Sergio.
Okay, great.
Yes.
Hermit. Okay, so I'm trying to share my screen, PowerPoint, okay. Okay, sorry, I'm now dealing with permissions. No, it's asking me to, that's not good. It's asking me to reboot. I don't want to do that if I can avoid it. Let's see. Am I sharing anything now?
Yes, you are sharing the AirMeet platform.
And now I'm still sharing the same?
Yes.
Yeah.
Sergio, you're caught in the same problem I had. Just export it to a PDF and then share the PDF.
Oh, no biggie. Okay. So apologies for that. Is a rather...
Yeah, that's kind of what I noticed when I was looking at it. So this might be a suggestion to all upcoming speakers to have your PDFs ready.
Yep. Okay, here we go. Can you see it now?
Yes.
Yes.
Okay. So I'm going to be representing three of the knowledge graphs, the open knowledge networks from the Open Knowledge Network effort. And these are SPOKE, a biomedical knowledge graph, Nowhere Graph, which provides area briefings within seconds for any region on Earth, and also the UFOKN, which is urban flooding knowledge graph. So I am the principal investigator of SPOKE, and I'm going to first present you with what SPOKE is, and then what are we trying to do in terms of integration with these other two, mostly with Nowhere Graph, which is where we started. But I should also mention that since the topic of this session is towards the meta-knowledge graph, I should also mention the effort that we're also part of on the NCAT's biomedical translator program, which is a prime example of also connecting multiple knowledge sources into one unified system, which is architecturally very different from this effort. And this is what I'm going to talk about here. How can we connect something that is biomedically oriented to something that is not? And what are the use cases that motivated this connectivity? As Chaitan mentioned before, it's all about the use cases. So SPOKE contains biomedical information. Biomedical information is probably complex like very few other areas. Here, I'm just showing the metabolic map. And if you can get a sense of how many concepts need to be modeled correctly in order to be able to represent our knowledge and to be able to reason over it is mind-boggling. So SPOKE is constructed as a property graph, and it contains millions of concepts of different biomedical importance or biomedical meaning, going from genes to diseases, how they are connected, to how diseases are connected to symptoms, to pharmacological compounds, biological therapeutics, how our metabolic and intracellular signaling pathways. So connecting, essentially what we're trying to do with SPOKE is build a causal path from a lower level of complexity, meaning the genome, which contains all the information to make a human being, all the way up to the human being, and see if we can connect the causality of the information of how it's encoded in the genome and represented at the higher order level. So this is a very large task, but we're a team very multidisciplinary, includes medical doctors, biologists, pharmacologists, computer scientists, people with expertise in knowledge representation and ontology development, and so on. So it really requires these many types of expertise, but particularly in this case, the biomedical expertise to model correctly the biomedical information that is available. So just to show you, there's many applications for SPOKE, but to show you some of the things that are incorporated, there's more than 9,000 diseases organized by the disease ontology in this case. You're visualizing a large branch of diseases and how they're connected. You're now visualizing the bacterial taxonomy. There's more than 5,000 bacterial species of importance to humans that are part of this large graph. And for example, there's a hierarchy of metabolic pathways and how a user can navigate logically from a general concept in pathways such as carbohydrate metabolism all the way down to glycolysis is one of those pathways. And then if you click glycolysis, you can go further into each of the reactions that are involved in this pathway. So essentially is connecting the compounds by the enzymatic reactions that transform one compound into another. And the long-term objective of something like this is to put together as many sources of information as possible that are well-known, almost textbook facts that are well-established, but they're impossible for any human being to be able to recall and apply at any given moment, things that a computer can do much better. So with this in mind, we always have the individual in mind, because ultimately this will be used to improve the understanding of the multitude of biomedical tests that we get when we go to a hospital and when we go to a clinic. And even doctors are struggling to put them together and integrate them, not only in a statistically meaningful manner, but also in a biomedically meaningful manner. So a model that understands the connections, the semantic relationships between these concepts, and can be used to integrate all this information. So we divide this into two main parts, the ectome and the endome. And the endome is everything from the skin in. So cellular, molecular, physiological, genetic, biochemical concepts that make up humans. And the ectome is the set of exposures or determinants of health that are outside of our control. Sometimes it's the environment, it's chemical exposures, is social determinants of health. So anything that can influence our health outcomes, but are not necessarily part of our own physiology or molecular biology. So we focus a lot in the endome first to try to integrate these sources of information. But this is where other knowledge graphs, such as Nowhere Graph, comes in handy, because Nowhere Graph has geolocation information for events that happen anywhere on Earth, anytime. So you can go back in time and ask, what kind of event happened here where my patient lives? So sometimes in this case, it's useful for us to say, well, this patient has this type of cancer. These are the genetic information that we can get from his or her biological samples. But these are the other factors that may contribute to making a diagnosis. And knowing where this patient lived and what happened there before may help better understand the situation of this particular patient or groups of patients if we do this en masse. So in order to be able to connect these two graphs, we needed to have at least one point of contact, because one of the graphs, if only contains biomedical information and the other only geographical information, then there's no point of contact. But what we identified is that, for example, geographical location will be also useful for the biomedical graph from a population based medicine. So we know, for example, from databases from the CDC, we know all the prevalence of diseases, even on a state by state or even further on a county by county level. So those are databases that we started to incorporate in the last few months to be able to connect disease prevalence and exposures and social behaviors into as outcomes of particular diseases, because by incorporating these geographical anchors, if you wish, then it will allow us to move to nowhere graph where we can learn more about it. So, for example, in Spoke, now one can make the link between this nodes in the left, which are representing locations, cities or zip codes, and these nodes in the right, which are representing diseases. And the connection is the prevalence of that disease in that location. Similarly, we can also identify the by using databases from the Environmental Protection Agency, which make available toxic repository information. We can locate the prevalence of certain chemicals in certain areas, and this is very useful for us to be able to link the chemicals which might be potentially harmful, even if we don't know it today, because we can connect it to their proteins if there's a database that exposes that information, and eventually to particular pathways that may be pathogenic. So we also were able to incorporate contaminants in drinking water. And again, these are when there's certain chemicals which concentrations exceed certain safety levels, they're reported, and we can link them to certain locations where those happen. So all of these are connections between Spoke and a geographical location. What this enables then, and this is the last one, is social determinants of health. For these, we're using the Social Vulnerability Index database, where we can connect determinants such as poverty or housing stability or unemployment to certain geographical locations. And again, those are important determinants of health as well. So what we're doing now is we've created a communication strategy to go from Spoke to nowhere graph whenever there is a common node. So if we're interested in, for example, knowing more about a particular location where a recent contaminant has been found, we can right-click on the graphical user interface and connect to directly the universal reference tag that will initiate the same search for that particular area in nowhere graph. Knowing that they're very different graphs, nowhere graph is a RDF, has an RDF architecture, so we had to overcome these technical challenges. But at least at this level, we can now go from Spoke to nowhere graph, and vice versa, from nowhere graph. If there's a region of interest and the user wants to know something more related, a biomedical question, what is the prevalence of diseases? Or I know that there was a fire here, can you tell me what the prevalence of cancer is in this area? And I want to know more about lung cancer. So then it goes to Spoke and starts exploring. So these are just baby steps into what we consider what is now a minimal integration level. In potential phase 3, we will dig deeper into a more fundamental integration between the graphs. So I think, and again, the last thing that I will mention is with the UFOKN, which is the urban flood knowledge graph, there's also great potential to connect with both spoke and nowhere graph. The connection is obvious because they're both geolocation based, but also with spoke because if there is, for example, a flooding event in a particular area, and there's an epidemic of, let's say, cholera, and someone wants to know more about cholera, then they can go into spoke and do those searches of more biomedical importance. So I think I'll stop here in the interest of time, but I'll be happy to answer any questions.
Thank you, Sergio. I don't see any questions in the chat. If the attendees have any questions, please either raise your hand or I think you can raise your hand here. Unmute yourself.
In the meantime, I'm trying to see how do I stop sharing.
You can never do that. So actually, Sergio, I have a question. I have a question, maybe a comment.
Yeah.
So we just heard about scientific paper summarization in the previous discussion.
Yeah.
And you mentioned, for example, outbreak of cholera. And I don't know anything about the technical area, so you should correct me where I'm wrong. But suppose there's a cholera outbreak in some part of the world, whether it's in the western part or the eastern, in the tropics or whatever it is. And maybe there are different characteristics. So maybe different people have written different papers about cholera outbreaks in the US versus in India or some such thing. So you could even imagine then connecting that to the summarization of the research papers, because you might want to say, who's done work in cholera outbreak in this region?
Well, I think that's possible. And to me, and I think Doug was very optimistic about the possibility of summarizing scientific papers, at least in the field of biomedicine. To me, this is very early on. I haven't seen yet a method that can do that well, because not even humans can do it well. So a scientific paper that gets summarized by 3 people, you will probably get 3 different versions of it. And so even the mental models that scientists have, biomedical scientists have about the same event could be modeled in different ways, and not always following logic. So I think that's still a very green field. But technically, yes, one could do the same for literature and location, and see where this research happened, and then tag the researchers to the reports of a particular geographical area.
Okay, that's an interesting point. There's some comments in the chat about linking nowhere graph to citation networks might be helpful in this regard. Yeah, I guess it's if basically the spatial component of it. I guess you could at least say that the study was conducted in such and such area. If the paper mentions that, then the nowhere graph can index into that.
Yeah, and I think it will help also, as now all papers will be written by ChatGPT. I think that this should be an opportunity to standardize a little more the literature that we write, and force us to use ontologies whenever we refer to anything. And so that will be easier to build better knowledge graphs from the literature in the future.
Okay. Well, I can see some issues there with spatial things, but I mean, yeah. Anyway, let's look at the chat. Microclaims. You want to make that, Mark? Antoine, do you want to say something about your chat point about microclaims? Maybe not.
Maybe not.
Is that actually something that could be looked at? Are people looking at sort of taking papers and breaking them down into microclaims?
Oh, he cannot activate voice.
Ah,
Uh,
I guess you have to. Yes, it is being done. He says, creating microclaims out of papers.
yeah, the one thing that I know it's been done now is to interpret figures from papers. So creating relationships from the actual images, and whenever usually the last figure of a scientific paper is the model that the scientist has in mind with arrows and concepts. So that could be read and a graph can be built from that. The challenge with that is that not always the mental image that we have of our model is grounded in reality or in hard information. Sometimes it's a very abstract model and does not really represent the information that we know. But that's an advancement.
One thing that's available actually is nano publications.
Yeah, nano publication.
Yes, they're basically small.
You're not. They can. Oh, you can. They can hear you through.
Oh,
me.
they can hear. Okay,
Yeah.
sorry. Sorry, it's Jamie McCusker. Nano publications are basically a way to kind of encapsulate the intent for paper claims that have been used for a lot of different knowledge graph management tools. And so basically it's a named graph with two other named graphs, one to provide the justification for the claim. So like the provenance of the paper usually, but also it could be like the links to evidence and things like that. And then the provenance of the actual artifact itself. And those have been actually very valuable both for, like I said, for kind of publishing scientific results of the original intent, but also for just knowledge graph management as a whole.
That's cool. Yeah, very interesting. Okay, I think we are at time. And hello, guys. Saw your note. You'll have to figure out how to get your voice in the because you're going to be on that panel session, which is, I guess, after the break. Okay, our next speaker. I'm trying to look for my schedule here.
Yeah, we are about to start the industry presentations, starting with Vinay Chaudhary from JP Morgan. We'll be talking about leveraging knowledge graph for legal search and supply chain.
One thing I should say is, we've not set this up with formal introductions, so please do introduce yourself as you go. Vinay, for example, was involved in Track A in the early days, so and then since then he has moved on. So Vinay, please introduce yourself.
Yeah, just a second. I'm having some challenges with the screen share. If I can figure out how to do that.
I think everyone, and sounds like if you have a PDF, it's a direct way of sharing, because when you say present to audience, it gives PDF as the option in case you're able to do that.
Yeah, so just I'm trying to figure this out. So if you could just give me a second. It's because I'm using my corporate Mac. It's I think you cannot share through the web browser, so I have to find a different way of doing it.
Okay, interesting. We'll give you a minute there.
So I just give me a second. I probably need to move the files locally, and then once I have the file local, then I'll be able to share.
Okay.
Hopefully. Okay, so let's see if magic happens.
Okay, while you're working on that, I think the administrator here, we're trying to see if anyone should be able to turn on their audio and participate, because I guess as a workshop, it'd be nice that, if people can ask questions, etc., rather than just being on chat. So when we come to the Q&A, we can give that a try. So are you ready, Vinay?
Yeah, I'm still in
Okay,
the process.
download.
Okay, here it is. I don't. Okay, I got this. It's downloading the attachment now. Well, I think the other option could be for me to a workspace.
We could change the order of presentations, give you more time
Yeah,
Can
to
you
get ready.
can you see my screen now?
No,
You
hang on,
can.
it's happening.
Yeah, you can.
Yes.
Okay.
Oh, it came and went, your slide. There you go.
Okay.
Okay.
Okay. Perfect. You can see my screen now, right?
Yes, we can see a slide. There you go.
Perfect. Awesome. So yeah, thanks, Chetan, for giving me opportunity to participate in this conversation. I used to be at SRI International, where I was part of many knowledge graph related projects, including various DARPA programs, including the KALO project that led to Siri. And also I was part of initiative from Vulcan, um, called Project Halo, as part of which we were creating knowledge bases from our textbooks. I spent a few years at Stanford trying to see if I could bring that research on textbook knowledge bases to reality. And some of that I will like to talk about today. Uh, at JP Morgan and Chase, I am part of a team called Machine Learning Center of Excellence. The team primarily focuses on machine learning, natural language processing, and knowledge graph applications. The team has a very strong mandate to do things that would directly help the business. So it has been very interesting for me to be part of this team because uh, I I'm exposed to a lot of projects which hit day to day working of the bank. And in fact, many of the apps that we use on day to day, like Chase Search or Chase QA, our team is supporting those products from the behind. There is going to be a presentation on various knowledge graph related projects later on in the afternoon. My colleague from JP Morgan, Yamani, she will be talking about those. But the current presentation, I'm going to primarily talk about the work I had done as part of the OKN program and my effort to find applications for that work in the context of finance. So the project we had as part of the OKN initiative was to see if we could uh, automate and scale the process of creating knowledge graphs from textbooks. And the driving application or motivating use case was an intelligent textbook, or to help students who are trying to learn from the textbooks. The task, the way we had set it up, was that let's say we have a sentence from the textbook, given an input textbook sentence, we want to identify the classes and relationships among them and create a graph out of that. So, for example, if you're given a textbook sentence, cytoplasm consists of jelly like cytosol within a cell, we want to create a knowledge graph of the sort showing here, where cytoplasm, cytosol, and cell, they are nodes, and we have edges between them, like cytoplasm has material cytosol, cytoplasm is inside the cell, and the viscosity of cytosol is jelly like. So we broke this problem into the problem of identifying the key terms from a sentence, and then identifying relationships between those key terms. And this is all work that was done as part of the phase one project. As part of that project, we were teamed up with OpenStax at Rice University. As you know, Rice has many open source textbooks. So we built a little system which had a term extraction piece and a relation extraction piece. For term extraction, at that time, we were using the language model called BERT. So we took the already available glossaries at the back of the textbook, and we fine-tuned BERT to extract terms from the textbook sentences. So as part of the training, we could feed a textbook into BERT, and we could get the key terms for each textbook sentence. In addition to term extraction, we also fine-tuned BERT for the task of relation extraction. We had a pre-built, hand-built knowledge base from our previous work with Vulkan that we used to train or fine-tune BERT in a distant supervision mode. Once the terms were extracted, we could feed them into the relation extractor, denoise the relations through a crowdsourcing kind of approach, and get the relations to construct the knowledge graph. And our vision was that we could sort of structure this as a pipeline, so that you feed a textbook, you get the key terms out, you put them through the human review, and then you run it through the relation extraction, you put it through human review again, and you validate this through inference, and you get a knowledge graph out. So this work is published as part of the AKBC conference. I have a reference here. You can read up in more detail. Um, we were hoping to do this as part of phase two project, but it just felt like a bridge too far in relation to some of the other things that were in the portfolio. So we didn't make it to the phase two, but uh, I ended up at JP Morgan, and one of the things I've been doing since I joined JP Morgan was, well, can I use similar ideas in finance? Like, are there other places where similar techniques could be leveraged? That's not the only thing that I'm doing at JP Morgan. This is one of the things I have explored. And there are two projects we pursued over last 1 year where similar ideas could be applied. And one of them is semantic search. This is semantic search over legal contracts. So when we are looking for certain terms within the contracts, those terms that tend to be very technical and highly domain specific. And I'll tell you about a little study that we did to see if we could apply the term extraction techniques to do semantic search over contracts. And then we also did a project on constructing supply chain graphs. And this was partly inspired by the phase two of the OKN program in the sprint, which was in the phase two of the OKN program. There was a use case on supply chains. And that information happens to be of a lot of interest to our business. And so we looked at how we might be able to use these automated methods to construct supply chain graphs from text. So I'll give you a little overview of that study as well. Okay, so now coming from a biology book, let's look at some finance type sentences. So these are sentences from OpenStack's finance textbooks. The process of forming a business as a sole proprietor is usually a simple matter. So here we are looking for sole proprietor. And it turns out that in finance, this extraction can be very domain specific. So, for example, if you look at the sentence shown next, one of the largest retailers in United States was started as a sole proprietorship by Richard Warren Sears as a mail order watch and jewelry sales. So, in the second sentence, we are primarily interested in kind of an e-commerce application, and here sole proprietorship is not very interesting, even though it's a key term, but we are more interested in the seller and the actual products that appear in the sentence. So the term extraction process or the problem can be highly nuanced, and it depends on the kind of problem you're trying to solve. And that's why it's not straightforward to just pick something off the shelf and use it. So for our project, we said, okay, well, let's see if we can train BERT in a highly domain specific manner. Uh, and again, the challenge is, where do you get the training data for key terms? So we said, okay, well, let's see if we can use finance textbooks. So it turns out OpenStax happens to have about 10 different finance textbooks, which kind of overlap with the domain that we were working with, and they had the glossaries at the back of the book. So we took the glossaries from the back of these the books, and we put them through BERT, and we fine-tuned BERT on them, so that BERT is now adapted to this finance domain. And then for our internal use cases, we had long documents with complex vocabularies on which we were doing semantic search. We fed those documents through this trained BERT extractor and searched for the terms that our people were looking for. Here you can see some results. The table above shows the training. So in the 10 books that we used, there were about 220,000 or so sentences, about 14,000 terms, which we put for training. The rest we use for testing. And as you can see, the baseline, if you just take BERT off the shelf, the precision recall and F1 numbers are really bad. But as you train them on these books, on this domain specific vocabulary, the performance shoots up quite a bit. So this was actually quite a success internally, and it's being used in some projects already. Now, let me switch to supply chain graphs. So in a supply chain graph, we are primarily interested in which companies are supplying raw material to others. And this, it turns out, is crucial information for a variety of use cases, not just within our business, but even within the design sprint. There were a lot of people who were very interested in graphs like this. It turns out that within JP Morgan, we use supply chain information, but we are primarily relying on vendor source data. There are a lot of vendors out there who provide this information, but it turns out that the information that they provide is often incomplete, and it's out of date. I mean, it lags what is already available in public information. It'll be like 3 months or 6 months before these vendor sources are updated. And the question our business people were asking was, is there any way for us to stay current with what's already out there? And an example, as hypothetical example is, well, let's take a 10K filing, which is with SEC. Can we mine information from the risk section to see if there are any impactful supply chain relationships that we might be interested in? So inspired by that problem, we came up with a very similar pipeline for extracting these graphs from the text. So the first part was, here, instead of term extraction, we need to do named entity recognition. We are looking for the names of the companies. You start from the input text, you extract the relevant sections which you want to process, and then you use an NER model to extract the organization names. And then for those sections, we would formulate supply chain relationships as a question. And so we turned that relation extraction problem into a question answering problem. Use one of the standard question answering model to extract the answer and see if the answer actually contains a company name. And that we could verify using the NER model. And then once we have the question and answers paired, we would deduplicate the results, and then we would put them in a graph. So there is already a lot of work out there on entity recognition, named entity recognition. There are two key pieces of references. One is the CON-LL 2003 dataset, where they took some news stories and adapted BERT and got a F1 score in the range of 93. And there is a separate paper where they were working on contract documents from SEC filings, and they were getting a score in the range of 82.7. So one could think that, well, why don't we just take these algorithms and just apply them to our problem, and maybe we'll get pretty good results. It turns out the results were not very good. When we took this and we applied it to some of the source documents we had, the results were actually quite miserable. So we then went about creating our own internal NER data set. We took some sample SEC 10K filings. We annotated them. We annotated about 1,200 sentences. And even though we were primarily looking for company names, but NER usually involves identifying persons, locations, and other miscellaneous entities. So we did the complete annotation so that we could work with the existing NER models. And here you can see the results. If we use a out-of-the-box model like a Spacey one, the NER model that you can find in Spacey, the results were like 0.33. And if you use it using CON-LLL only, you get 0.67. But if you do combine both CON-LLL and Wikineural, you get an F1 score of 0.72. This was a fairly preliminary work. We produced a little supply chain graph as an experiment, as a summer project, but there were quite a few problems that still needed to be solved. One of the issues that comes up is that in the source documents we were looking at, the only one organization will be mentioned. They won't mention both the organization, because we are looking at the report of one particular company, so that company's name won't be mentioned, right? And you do have to still disambiguate the company names because they are mentioned in many different ways, and you can't find any existing data set for extracting these supply chain kind of relationships. So for the relation extraction, as I mentioned earlier, we turned that problem into a question answering problem. And we had a suite of questions, and some of which you are seeing here. So we asked the question, who are our suppliers? Who do we supply raw materials to? Which companies depend on us for their supplies? Which companies supply to us, etc. And for question answering, we used the Roberta model, which was already fine-tuned on Squad. We took the top 10 candidate answers and filtered those out that didn't have company names, and then deduplicated the answers. On this slide, you can see some examples of the kind of extraction we were able to do. Let's just take the first line here. In the first line for this company, Sunesis, from this sentence, if we ask this question, who are our suppliers, you do get Catalenta Farm Solutions and Catalent, both of which happen to be correct answers and suppliers of this particular company. Okay, so as I mentioned, this was a kind of a small experimental prototype project, and it stopped with this little study. But it was pretty clear that if this work has to be scaled to much bigger, creating much bigger supply chain graphs, we do need to improve named entity recognition. The F1 score of 0.7 is not bad, but I think it's still quite noisy to be used in real world situations. We need to scale up the extraction. We build these, small supply chain graph fragments, but in principle, you could create a global supply chain graph by merging these individual fragments and potentially even merging this data into externally available and externally sourced supply chain graphs. My last slide. Yeah. So the just to conclude, the for building blocks for creating knowledge graphs of text from text include a key phrase extraction, named entity extraction, relation extraction, some of which we explored in the OKN phase 1 project. But we've also found that the domain specific training continues to play a fairly critical role. And since my work at JPMC, we have been kind of experimenting with various financial and legal documents and finding that um, domain specific training just is very essential. You really can't have domain general solution. You have to specialize and customize the solutions to the domain.
Well, thanks very much, Vinay. There's already a question for you in the chat, which is, could you explain the fine-tuning process? Glossary is a list of terms. How do you use this to fine-tune BERT?
Yeah, so I think the fine tuning is our fine tuning work is published in the AKBC paper that I mentioned. It's if you go to 2021 AKBC, there is a lot of detail on how we went about fine tuning BERT, and it's explained in a lot of gory detail. And if you need more detail, please feel free to write to me.
All right, thanks. In the interest of time, we'll move to the next one. We're right on time here. So our next speaker is Ora, who actually doesn't need much introduction at all to this crowd, I think. But Ora, whatever you want to say to introduce yourself, please do so. It's yours.
Let me first confirm that you can see my slides.
Yes, can see it.
Okay, great. Well, thanks for inviting me. I am going to talk about interoperability and open standards. And the reason for this is that it was something that kind of worried me during the innovation sprint last year. And so I will offer some thoughts about that. So just as an introduction, I work in the Amazon Neptune Graph database team, but I've been doing this stuff for a very long time. And I guess what I really want to say here is that I kind of have been doing AI for a very long time. Lived through the AI boom in the 1980s and through the AI winter in the 1990s and survived. And the reason why I'm saying that will be evident at the end of this talk. So first of all, this is not a talk about large language models, at least mostly not about that. So this is really what I want to talk about. So of course we have this kind of tradition of building silos, and I think that we are kind of at the risk of repeating this. So the old silos having been sort of these data that was controlled by a single application, and if you were really lucky, you got some kind of a custom API to access that. And I feel like these single purpose knowledge graphs without easy opportunity for interoperability or interlinking are kind of the new silos. And I think that this is something we really should avoid so that we don't repeat what happened in the past. So of course, why do we need interoperability? So we have common formats that enables information interchange and common query languages that hopefully enable some type of interworking, and also free users from vendor lock-in. In the Amazon Neptune team, we are big believers in open standards, and so Neptune as a graph database, you talk to it through a Sparkle endpoint, and so it's easy for you to bring your data there from other applications. But also, if you're not happy, you can move your data to another graph database. So this is all good, but we also need common shared semantics. And sort of related to that, we really need to pay close attention to how we identify things, because that's really kind of the basis for building knowledge graphs. My belief is that those standards or technologies that are not designed for sharing and interchange of semantics, we should just reject offhand, because those will just take us back to the old days of silos. So in some ways, today we are here. This is, of course, the Tower of Babel. So we build systems. Some people see APIs as kind of a panacea for building distributed and loosely coupled systems, but they really lead to something like this, where everybody's talking and nobody's really understanding. And so generally speaking, we have a situation where one system uses some data, articulates the semantics for that data. If that data moves to another system, we kind of re-articulate or redefine the semantics. And I look at this as sort of a form of technical debt. It's error prone, and we shouldn't be doing it. And of course, we keep repeating this. Every system and that we take the data to re-articulates the semantics. And I think that oftentimes when people say, okay, give me access to your data, if you only give them access to the physical bits, you're not doing them much of a service. So you also have to give them access to the semantics of that data. So I would like to see something like this, where the semantics kind of moves with the data. It would be sort of an ideal situation. Of course, it's something that's absolutely vital when we start building these interconnected knowledge graphs. So, as a sort of a point of terminology, the way I think about this, I don't take a very formal a view of semantics, but I would say that semantics is really sort of definitions of how the data behaves and how software can interpret that data. And ontologies, of course, are the means of communicating the semantics. So now, of course, we have all these these open standards that we've had for a long time. The so-called W3C semantic web stack. These are very mature specifications. We started work on those back in over 25 years ago. And of course, more recently, we've sort of seen this, what in some ways I think of as a competing set of, well, they're not really standards, but the technologies anyway. So the so-called labeled property graphs. The big difference here being really that labeled property graph databases have been designed more like conventional databases. So knowledge interchange has not really been a priority. You sort of operate in the confines of your database. You make a closed world assumption and all that, and so building these systems that distributed and federated systems that connect to one another is always sort of an engineering proposition. You need to integrate with someone else. It's an engineering problem, and it shouldn't be that. RDF, of course, was specifically designed for interoperability and knowledge interchange. It has relies on URIs or IRIs for identifiers. And it also, what's really important and what people often miss is that RDF has formally defined semantics for graph merging, which makes it really easy to bring in data, connect to someone else's knowledge graphs, and so forth. And it has schema languages for building ontologies. And Sparkle, as the query language, really was something that was intended to be like the sole means between an application and a knowledge graph store to communicate with one another. What's really important is to understand that Sparkle also supports federated queries. And so when you take these things, Sparkle really makes it easy to build these kind of loosely coupled knowledge systems. Now, of course, those specifications are not enough. You also need vocabularies, or so when you're building your ontology, you don't necessarily want to start from scratch. There are useful common vocabularies that you can use, and RDF was designed for extension. So if something is not what you need, you can always extend. Now, there's also some emerging stuff that is worth mentioning here. So W3C is working on something called RDF Star, which will make it a lot easier than before to use RDF for things where, for example, you want to capture provenance or lineage of data, because you can make statements about the statements that your graph makes. And in some ways, this brings RDF kind of closer to labeled property graphs, because you can think of these statements about statements as sort of a generalized version of what the LPG is called edge properties. And of course, this is the idea here is that we make it a lot easier than the old mechanism that existed in RDF, which we called reification. It's kind of awkward and unpopular, and one reason why it's unpopular is that it's probably the most misunderstood part of the original RDF specification. I recently looked at the consecutive drafts of the original RDF specification, and what's interesting is that in the first public working draft from '97, reification was mentioned almost immediately. It comes right in the beginning of the specification, and then in consecutive drafts, it keeps moving further back in the spec. So we're going to fix this now. I'm chairing the RDF Star working group, and we're making good progress for building this. Another interesting ongoing thing is that ISO is in the process of standardizing a query language for labeled property graphs. And it's loosely based on Cypher. What's, in my mind, a really important part of this is that we'll finally have an actual schema language for labeled property graphs. So we can see that there's now ongoing work on both sides. So on the RDF side and on the labeled property graph side. So the question is, where do we go with this? And I feel that the fact that we have these two graph meta models that are both popular is kind of a rift that, in a way, sort of causes confusion among users and people building graph-based solutions, and it sort of continues to plague the whole industry. I think it's a hindrance to adoption because of the confusion, and our graph database, Neptune, supports both of these, but today you have to choose which one you're going to be using, and then that dictates what query languages, for example, are available to you. I sort of think that the real issue here is that whether you look at the graph as sort of a logical representation of something, or whether you think of it as a sort of a literal data structure. Now, both are useful things. Of course, in the software industry, what we do is we build data structures and we write code to manipulate them. And so if you think of your graph as a data structure, then a graph database gives you the means of building larger data structures and manipulating really complex data structures. But on the ontology side and on kind of the knowledge graph side, you really want to think of the graph not so much as a data structure, but sort of a logical representation of something. So having said this, it should not be hard to choose between the two. But the thing is that neither one of the set of technologies is perfect. And then of course people's personal preferences also come to play here. So what are we doing about this? So we are engaged in this project called OneGraph, where we are basically trying to make the rift go away. So this is a unifying model between RDF and labeled property graphs. It is not an easy solution that we'll have for this, because there are some differences between these methodologies. RDF star work is sort of a very significant step in the right direction, but will not completely get us there. At least the way we look at where the working group is going today. The interesting thing here is that once this is realized, and we are working on an implementation, and this implementation will be available in the future. What we have is that we have kind of benefits on both sides from this work. So oftentimes when I look at people use labeled property graphs, they tend to reinvent things that already exist in RDF. Now you don't have to do this anymore. Now, on the other hand, Sparkle as a query language is such that there are queries you cannot express in Sparkle. It's not a recursive query language. So my big expectation here is that I will one day, very soon, be able to run Gremlin queries over RDF and write more expressive queries than I can today with Sparkle. Okay, so that's my kind of pitch for interoperability. We need to build large knowledge graph systems. We need to connect them, and so now comes the question of large language models. So I'm hoping and I believe that knowledge graphs can really be sort of the grounding for large language models. We need curated, trusted sources. We need the ability to explain the results. We need to be able to track provenance and lineage. We need to eliminate hallucinations. Here's a sort of a kind of a chilling example of hallucinations. So basically, somebody asked ChatGPT to compile a list of faculty members who have been accused of sexual harassment. And he finds one of his friends on the list and thinks, what the heck's going on here? And turns out that the explanation that ChatGPT gave where this incident happened, it was some school trip that actually had never taken place. ChatGPT gave a citation to another Washington Post article as evidence of this. That was a completely fictitious article that had never been published. And so, in a way, sort of the only thing that was real was that a real person was named. And so when I look at the kind of the long span of AI, the history of AI, there have been these cycles where we get really excited about some technology, and then there is potential disappointment and hangover, and I think that we are at a point like that right now. We can everybody is really excited about generative AI. I think that the lay people have potentially completely wrong expectations about this technology, and we're at a perfect moment where we can really mess things up again. And I don't want to see another AI winter. I think the trustworthiness of technologies is the key. And my belief is that the only way we can kind of reach this trustworthiness for these systems is that these language models are grounded in knowledge graphs and sort of curated knowledge that we can trust. And I'm happy to entertain some questions if anybody has those.
Great. Thanks very much, Ora. Very thought-provoking. Are there, I can't imagine that there aren't questions, but one thing you can try if you have a question is try to raise your hand and the administrator will bring you on stage so you can actually ask your question. You don't have to type it up. And while you're thinking of those, I think you sort of answered this, but I was going to ask you, so suppose one was starting a set of projects soon.
Hypothetically.
Hypothetically, you talked about RDF star and the one graph idea and so on. What kind of guidance would you give to projects if you wanted to, get them all to be sort of copacetic, to use an old term?
Well, okay. So if you use RDF star today, you're still building on ground that may move from under you. So, exercise caution there. We're working as fast as we can in the working group to get to a point where we have a stable specification. We're not quite there yet. As for the one graph, so we are in the Neptune team. We are working on an implementation, and this implementation will be available. I can't, unfortunately, name an exact date when that implementation is going to be available. But what it will give you is that, so today, if you want to integrate, and we already saw an example of this, you want to integrate an RDF-based knowledge graph and an LPG-based knowledge graph, it's an engineering problem. It's a project. What we'll have once OneGraph comes along is that now you can actually write federated queries that access also LPG graphs, and all of this becomes easier. Now, there's, like I said, this is not an easy solution, but we will succeed. And we will have this, and also we don't intend to keep this proprietary. Like I said, we believe in open standards, and so the whole OneGraph specification, it will make it open and available. We're hoping that this is sort of a direction for the whole industry, graphs and knowledge graphs, rather than just for us.
Yeah, I do have a follow-up, but I want to, let me see if others have. Okay, there's a question here. How can we contribute to the OneGraph effort? I just brought up your paper, and it had a bunch of authors, many from your organization, I think, but people want to know, how do you contribute to this effort?
Yeah, that's a very good question, and we haven't quite nailed down what would be our preferred way, but I would say that at this point, get in touch with me and we can discuss. I'll put my email address here in the chat. So super difficult to remember. There you go.
I'll actually give you an answer for you, which is get ready to become part of the testing community.
We're very interested in supporting the overall community, and interested in sort of public-private partnerships. keep talking about this within the team all the time. So
Okay.
it sort of comes from our belief in open things.
This question is too tempting not to ask. I'm going to ask you. Do you have any thoughts on how to incentivize leading AI tech companies to care more about the truth and not spread lies?
Yeah, it's I don't have a silver bullet for that. We care about the truth and sort of full disclosure in some sense. I think that somebody needs to paint the ugly enough picture of the new AI winter that's coming if we don't do this right.
Yeah.
Because I promise you, it is coming potentially. So we just need to make it clear to people that what are the expectations of the technologies as they exist today, and what is the direction where we need to go to avoid this disaster.
Yeah, that's a good point, and I do think big regulation may be coming down the pike if you don't do things properly.
Well, okay, so right, so there is this open letter that something like 30,000 people have now signed that wants to put a moratorium on the development of these large language models and generative AI, and I think that's absolutely the wrong thing to do. That cat's out of the bag, or how do you say that? The train left the station. So none of this has worked in the past by saying don't work on this technology. Instead, I think we need to work on technological solutions to put guardrails and safeguards on something like the large language models, and try to understand how we can make this better, not stop it, make it better.
There's just a comment. NREL, the National Renewable Energy Lab, has started with RDF on Neptune, so they would like to engage with you all, I guess.
Absolutely, we are very happy to talk to you, and just my email's there. Get in touch. We'll talk.
Okay, if there's any last pressing question, we're right on time, which is fabulous. Any last question for Aura? Otherwise, of course, we're all here. So we're going to take a break now until, what is it? Till 11:30, I think. And so we'll be back in 10. Hang on, I'm trying to check.
20 minutes.
Sorry, in 20 minutes, I think, right?
Yes.
Okay, in 20 minutes. So, so we'll be back at 11:30. Yeah, that's 20 minutes. Okay. And Aura, you can come and join us here.
I will come down. Yep. Great.
The next will be the federal agency panel folks, and so make sure that you're able to come backstage for that. And so see you in 20.